Hi, everyone, and welcome. As we have you all joining today, I'd like to welcome you all to the Teens in Action Forum hosted by Teens in AI. So, my name is Alana, and I'll be your host and facilitator today for today's session. I'm really happy to be here with all of you, and we're going to be exploring some really exciting topics and ideas in technology, AI, and machine learning. Today's particular session is going to be an interactive guide on machine learning and AI. So for those who may be new to us and haven't heard, Teens in AI is a multi-award winning social impact initiative that was launched at the United Nations AI for Good Summit back in 2018. Our mission is to empower the next generation of leaders and innovators, and over the years, we have now reached more than 20,000 young people across many settings in over 95 countries, and we are hoping to reach even more. So this session is brought in partnership with you from Sage, an organization that is committed to inspiring a new era of AI leadership. And together we're paving the way for more young people to bring a difference in the world of AI. But before we get started, I have some news to share with you. At the end of the workshop, we're going to be revealing a special early discount, as we did the last session, on our next upcoming Summer AI for Good Incubator program. It's an amazing sustainability-based Take-a-thon style bootcamp program. And if you're passionate about AI and you want to take your skills to the next level, this is definitely an opportunity you don't want to miss. So stay tuned till the end of the session, and we're going to share more details at the end with more brand new courses that we're also going to announce. So what will this session be really about? So you're going to learn about machine learning and AI with a special focus on artificial neural networks and particularly the multi-layer perceptron, which is MLP. I hope I said that correctly. We're going to learn a little bit more about Pete's journey into AI, and I'm telling you, it is very impressive. And then we're going to be learning a little bit more about machine learning, and he's going to give you a bit more information about that. Of course, at the end, you'll be sharing your thoughts and your feedback with us, which is always my favorite part of the forum. So before we start, I would also just do some housekeeping on how we're going to be working today. So keep an open mind and be curious throughout the talk. Don't hesitate to share your ideas. This is a judgment-free zone. All questions and comments should go through the Q&A session, which will be seen at the bottom of your screen. And if you have any additional comments and you'd like to share some notes with us, you can share that through the chat. And I see, which is really, really engaging right now. It's lovely to hear from you all. And just to also respect everyone's opinions and to keep the conversations positive and constructive. So now it is time to get started, and I'm going to introduce our speaker for today, who is Pete Husmayr. So Pete is from South Africa, like me, but he's currently based in the UK, and he is passionate about technology, engineering, and sports. He is the co-founder and chief innovation officer of Sportable, which he founded back in 2016. He has an incredible educational background. He has completed engineering degrees in mechanical engineering, computational mechanics, and nuclear engineering, including a PhD in space nuclear engineering from Cambridge University. And while he was at Cambridge, he spent 4 years of that working for the NASA Marshall Space Flight Center and the Center for Space Nuclear Research, which was based at the Idaho National Labs. Now he is applying his passion for sports and problem solving as the Chief Innovation Officer and member of the board for Sportable, which is also in collaboration with Sage. So let's give us a warm welcome to Pete, and let's start. Over to you.
Fantastic. Is it over to me? Should I start sharing my screen?
Absolutely, when you're ready.
Okay, I'm ready. Let me just get to my slides. Hi, everyone. It's an absolute pleasure to be here. Thank you for having me. Today, I'd like to give you maybe something a bit different than what you've seen before. I'd like to actually get into the nuts and bolts of what deep learning looks like. And so, yeah, let's kick it off. I'm going to share my screen. Just bear with me for 1 second. Here we go. Okay, can you all see it? Fantastic.
Yes, we can.
All right, guys, artificial intelligence and machine learning, they have rapidly become integral parts of our lives. You encounter them daily, often without even realizing it. Have you ever wondered how your smartphone predicts the next word you're about to type? Or how Netflix knows exactly what the next show you might want to watch is? Maybe some of you have even used Siri and Alexa or an equivalent kind of thing to ask for directions, and they've flawlessly guided you to where you needed to get to. All of these technologies are powered by AI and machine learning. So today we're going to dive a little bit deeper into how machines actually learn and the methods they use. And by the end of this talk, I hope you'll have a solid and hopefully intuitive understanding of AI's foundations, particularly the exciting role played by neural networks like the multi-layer perceptron. So let's get started. How do machines learn? Machine learning has become an essential tool for solving complex real-world problems that traditional methods struggle to address. So let's consider a few examples. Take the stock market. Predicting future stock prices is notoriously difficult. And of course, it would be difficult because if it weren't, we'd all be making enormous sums of money, but we aren't. And the reason is because there are an enormous number of variables that interact in very complex ways. Now let's go to an example from sports. Selecting the best athletes for a team or predicting an athlete's performance is again incredibly difficult because there are lots of variables that interact in complex ways. Now, take for a second the challenge of classifying objects from an image or from video. Picture in your mind a person sitting on their couch with a cat sitting in their lap. Could you even imagine writing a software program to detect the boundary of the cat, to detect the boundary of the person, to somehow disentangle the two as being separate objects, and then to ignore the couch and ignore the rest of the room? It's a mind-bogglingly difficult challenge. And then what about generating realistic conversation like ChatGPT does so well? How would you even begin to do that from a software perspective? Now, these are all things that machine learning and AI excel at. Why? Because what we're talking about today, machine learning and AI, is a systematic approach to finding patterns in high-dimensional data through learning. Now, if we want to get specific for a moment, machine learning tackles a variety of problems, each requiring a unique approach. So let's explore some of the primary types of machine learning, of the machine learning tasks. First, we have binary classification, a simple yet very powerful and important technique. Binary classification involves categorizing data into two distinct groups. So let me give you a super simple example that is immensely important to industry. And in fact, a technique like this that I'm about to describe might even underpin billions of dollars of transactions. Now, imagine you have a factory and the factory needs to process millions of tomatoes from a number of farmers. Now, these tomatoes are streaming through on a conveyor belt. And now what you want to do is sort the tomatoes into ripe and unripe. Maybe the ripe ones are red and the unripe ones are green. And if you can detect an unripe tomato, you can use a blast of air to blow the unripe tomato off the conveyor belt. This is binary classification. It's a simple but very, very important task. And there are many applications of binary classification apart from just smart sorting. Next, we have clustering. Clustering is a powerful machine learning technique, and I've indicated clustering in the diagram on the top right here. It's a powerful machine learning technique that you use particularly when you're working with unstructured or unlabeled data. So imagine for a second that you find in your drawer at home a hard drive, and on that hard drive, there are thousands and thousands of photos that you've taken on your mobile phone. Now, some of these photos, and none of them have names, so that's completely unlabeled. Now, some of the photos are pictures of you. Some of the photos are pictures of you and your friends. Some of the photos are pictures of you with your family. And some of the photos might just be photos of cars or cats that you've seen on the road. Clustering is an approach that would help you to, in a systematic way, to group the photos by similarity. And it helps you to discover structure in the data that you didn't know was there. It's a really important technique that will then help you with further analysis, labeling, or decision making. Next, we have regression tasks. That's this bottom left image here of the straight line graph. Now, regression tasks we're going to talk about a lot in this presentation. Regression is the art of fitting a model to input data that will allow you to make predictions about new data. A common example is predicting house prices. So the regression algorithm might examine a number of different factors. So let's say you're trying to figure out how much a house should cost. Maybe you would look at the location of the house, the size of the house, and the number of bedrooms. Now, a regression task would try and find a function that finds a relationship between those three variables and then gives you a price. Once your model has been trained properly, you can then feed in new data about different houses, and it should give you a good estimate of the house price. Now, in this image on the slide, the data are these blue dots. The green line is the function that we are fitting to the data. Now, many of you will have come across straight line graphs before, y equals mx plus c, or in slightly different notation I've written here, the function of x is equal to w naught, a weight, plus w1, another weight, multiplied by the input. We are going to be talking about weights a lot in this presentation. And you can think of the coefficients on your straight line graph as weights. And if you're trying to find the best straight line to fit through a data set, you're finding the best weights for that straight line. Now, finally, I've illustrated with a picture of a man pulling his hair out here. We have dimensionality reduction. This sounds super complicated, but actually what it is a method to make things simpler. Imagine trying to choose the best starting team out of a group of football players. The key things to look at, clearly, are things like their fitness, how many goals they've scored recently, their past performances, and their cohesiveness as a group. But would you look at variables like their favorite TV shows? Does it matter that player B has an aunt and two uncles? Does it matter that player D has a cat? Of course not. Dimensionality reduction is a technique to remove variables that don't matter so that we can focus on the things that do. Each of these machine learning techniques addresses different problems effectively. However, the real power lies in knowing when and how to apply each approach. So, in all the examples I've just given you on the last slide, if we really think about what we're doing, the essence is to take something, which we'll call an input, and transform it into something else. We'll call it an output. So in the example of the house, we take an input, which is the house's location, size, and number of bedrooms, and we transform that into a price. Or we take your photos as an input and we transform them into a group of photos that all have similarities. Or we take tomatoes as an input and we transform them into two sets, a set of ripe tomatoes and a set of unripe tomatoes. Now, this thing in the middle that does the transformation is super important. We call it a function or an unknown function. And the essence of machine learning is to figure out what that function is. Now, to make this slightly more relevant to you, let's go back to the example of a straight line graph. At the bottom of the slide, I've reminded you that a straight line graph is a function. It takes the input x, and then the way the function manipulates that input is it multiplies the input by a weight, in this case m, and then it adds what we might call a bias or a weight. They're roughly the same, but you add another thing to it, and you create y, which is your output. So this is what we're trying to do in machine learning. We're trying to find weights that define functions that best approximate the learning space that we're trying to generalize. So let's shift gears now and get into the specifics. Formula One, like all sports, is about competition and high performance. The difference between winning and losing could be 1/100th of a second. So let's think for a second about how we can help a Formula One team choose the best possible car for a given race. Now, these races take place all over the world. Some of them are in locations that are extremely hot. Some of these races take place at high altitude where there's literally less oxygen in the air for the engines. Some of the locations are often wet and rainy. We need to help the Formula One team take all of these factors into account and more. So let's consider factors like track surface, weather conditions, tire choice, aerodynamic settings, fuel efficiency. And let's try and construct a model that will predict the average lap speed of the car with those inputs. So our goal is to create a model that takes in, say, for example, the driver. Now, we can label the drivers 1, 2, and 3. It takes in the altitude of the track. It takes in the expected weather on the day. We could call hot and sunny 1. We could call cool and dry 2. We could call rainy 3. It takes in the chosen tires. And then it outputs a predicted average car speed at that track. Now, how can we do this? One answer, because there's always many ways to skin a cat, but one answer is to use regression. Let's quickly go back to our example from slide 3, predicting the house price. In that image, we were trying to fit a straight line to noisy data. And that straight line was y equals mx plus c. We were trying to find the weights that made that line best approximate the data. Now, in this example, which is a much more complex example, because we have many, many more factors that may interact in ways that we don't understand. So we're trying to fit some unknown function, but to what data exactly? Well, data is very important, and you can believe it, the Formula One team will almost certainly have about 20 years worth of racing data that we can use. So we can train our model using that data. So imagine for the last 20 years, we know exactly what car the Formula One team put into the race, and we have the lap time of the car for every lap in the race. And so we'll know the average car speed. So we've got our inputs, but we also have the output. We know the speed, and we can use that knowledge to update and train the weights in our model so that we can make a model that then can predict car configurations that it's never seen before. Now, if we tune the model over thousands and thousands and thousands of races, it will start to learn the patterns in the data. And this is what we're trying to do. Because if we can create this model that can then predict the average car speed for configurations it's never seen before, then our Formula One team can try out many different kinds of configurations and just simply pick the best one that is right for those conditions. Now we can really get into the details. We're going to talk about something called the multi-layer perceptron. It sounds very complicated, but don't worry. It is possibly one of the most fascinating examples of deep learning that is accessible. And it is the workhorse of machine learning regression. The multi-layer perceptron is a powerful and versatile type of artificial neural network that has significantly advanced the capabilities of machine learning. Imagine the neural network as a simplified model of the human brain, comprising interconnected neurons. Now, these neurons I've shown as these dots in the bottom right-hand side. We've got the green dots, the purple dots, and the red dots. The neurons are organized into layers, and the information is fed forward through the network layer by layer. These layers, the way the model is architected also is that you have an input layer which receives the input data. So those green dots are where we input the known information. So we're going to input their driver, altitude, weather, and tire selection, say, for example. Now, then we have the hidden layer, and then finally the output, the hidden layers, and then finally the output layer. So let's talk about what the hidden layer sees. Now, I have labeled one of those neurons as 1 in the image. So this purple neuron in hidden layer 1, what does it see in terms of those inputs? Well, when you initialize a neural network, you'll just initialize all the weights as being effectively some random uniform distribution. Now, one of the things that we can do is we can look at this neuron number 1 and what it might see. For example, it might see 3 times driver minus 2 times altitude plus 10 times weather minus 1 times tires. That's maybe what it might see. Those numbers that I gave you, 3, minus 2, 10, and minus 1, those are the weights that connect that neuron to the input layer. Now, if we go to the neuron below it, it is also connected to the input layer. So it will also have those 4 weights. So the first hidden layer is connected to the input layer with 5 times 4 equals 20 weights. Now we need to find these weights somehow. But if you look, there's also a second hidden layer. Now that second hidden layer is connected to the first hidden layer. Each one of those neurons is connected to the 5 behind it. So there are 5 times 5, which is 25 weights. And the same is true for the third and the fourth hidden layers. All in all, if we add up all the weights, there are 100 weights that we need to find. And there are also another 21 things called biases, which are basically like weights. So in total, we have 121 things that we have to fit and find to make the model fit the data. Now, just think for a second how much more complicated this is than the simple straight line graph. In the simple straight line graph, you had y equals mx plus c. You've got 2 weights. That's it. We've now got 121 parameters. So you can imagine how complex this function can be and how complex and rich some of the patterns are that it'll be able to find in the data. Now, before I start talking about how we actually find these weights, let's just talk a little bit about where the magic happens in the multi-layer perceptron. The magic happens in the hidden layers. So those neurons that I've labeled in purple. Now, something that we've got to talk about now is I spoke about, that neuron number 1, maybe it sees 10 times driver minus 2 times altitude plus blah, 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 blah. But what does it output? Well, the way that neurons work is they need to be really activated before they will output anything. So what the neuron has is a thing called an activation function. Now, this function is designed to be very similar to how the neurons in our brains actually work. And I want to describe the way the activation function works, kind of like this. Imagine you're wearing your headphones and you're listening to music, and your friend comes to try and speak to you. You know, if they just come and talk to you quietly, you'll ignore them and you'll do nothing. If they come and kind of, elbow you a little bit, and you might just go, come on, go away. You'll be kind of at an intermediate state of agitation. But if your friend comes and really shakes you and starts shouting at you, you'll take your headphones off and go, what? That is kind of similar to how the activation function works. The activation function will do almost nothing if you don't give it a strong enough input. And that's the way our sensory neurons in our brain work. If you activate it a lot, it will fire. And this is a non-linear function, and it's very important. It can't be a linear function. It's a non-linear function, which is absolutely crucial. And we're going to get onto that in a slide or two from now. But its non-linearity is what allows the network to learn complex, intricate relationships within the data, far, far beyond what you'd be able to learn with simple linear patterns. In fact, the non-linearity will allow us to essentially model something as complex as the human brain. But let's now go back to talking about how we find these weights. Now, in the diagram here, I've explained basically how you find the weights. We're not going to go into the exact mechanics of it, but we can talk about it in the questions afterwards. Essentially, let's go back to the Formula One example. We've got 20 years worth of data from our Formula One team. Let's randomly select half of the data. And what we're going to do is we're going to feed into the model known car configurations, and it's going to output an incorrect answer. It will be wrong. And luckily, we know how fast the car was for that configuration because the Formula One team kept track of all this data very well. So based on how wrong the model is, we then go make an update to the weights. And there's a special mathematical procedure to update these weights based on how wrong the model is. And then you feed in some more data into the input, and it's still wrong. So you make an adjustment. And you feed data in, it's wrong, you make an adjustment. Now, over time, the model will get slightly less wrong because as you've been tuning these weights, it's starting to explore the complex landscape of this function that we're trying to find. And it's getting better and better at predicting the underlying training data. Now, over enough training cycles, eventually, it is predicting numbers that are very, very close to being correct. And so the error between what it's predicting and what it should be gets very small. And now our updates to our weights are only little, only very small. So at some point, we're going to stop and we're going to say the model is trained. And it might be a good idea to then test the model on a validation data set, maybe the other half of the data set, to check how well it's generalized to data it's never seen before. But if you've done everything correctly and the model has been updated appropriately, you've now got a powerful tool to put in the hands of the Formula One team. Because if the model has generalized correctly, you can put in any car configuration you can think of. You can write a computer program to basically iterate over every conceivable car configuration and literally just pick the best configuration for the highest speed. So what I'd like to do now quickly, though, is just address the key areas of maths that you're going to need to pay attention to if this is something that speaks to you as a professional calling. The first area is called linear algebra. And, personally, for me, linear algebra is, easily one of the crown jewels produced by the human mind. It stems from an incredibly simple question. If I have two straight lines, do they intersect? Or are they parallel? What about if I have three planes in three-dimensional space? Do the planes intersect in a single point? Do they intersect in a line? Do they intersect everywhere? Are they the same plane? Are they parallel? Do they intersect nowhere? Now, these incredibly simple questions lead us to systems of equations, which you've probably done when you're finding the intersection of two straight lines. But systems of equations then go on to become matrices. Matrices then become fascinating properties of matrices, like spectral properties and so on. Matrices then become tensors, and tensors are essentially higher dimensional matrices. And this is a beautiful and powerful subject in mathematics. And if you get all the way to matrices and tensors and you don't want to do machine learning, you can do general relativity, quantum mechanics, you can do anything else you want to do because it's used everywhere. So pay attention to it and make sure you have a strong foundation. Now, the second area is calculus, more specifically matrix and tensor calculus. So we spoke about matrices in the just previously now in terms of linear algebra. You can do calculus in linear algebra too. So matrix and tensor calculus is very important because I didn't talk earlier about how we update the weights in the model. And this is where calculus comes in. To find the weights of our model, it basically involves taking the derivative of the weights in the model with respect to the error in the prediction. And this is the beauty of it, because that is essentially what you do. And then you're able to back propagate a correction to the weights. So back propagation is the technical name for how we update the weights in our model systematically. And I don't think it's a stretch to say that back propagation probably underpins what is becoming a multi-trillion-dollar industry. So moral of the story is pay attention in calculus and learn to love it. So where I want to get to now is, and this will be the final slide before we begin to talk and have a discussion. You can ask any questions you like. But this, I think, is incredibly important result. It's the universal approximation theorem. And it's got really powerful implications, to be honest. So in the example we spoke about, namely the multi-layer perceptron, the conditions are, if it has a nonlinear activation function. Now remember what I said about the activation function. If you don't input enough strongly into it, it won't do anything. And then it's got a transition region, and then suddenly it fires and it's outputting as strong as it can. If your model has a nonlinear activation function, like the one I showed you, and if it has at least one hidden layer, then that model will satisfy the universal approximation theorem. And what this means is that that model will be able to represent any continuous function to arbitrary precision, just as long as we have enough weights in the model. Now, this is incredibly meaningful because what it means and what we are starting to see already out there in industry is that we might one day be able to create a numerical model of the human brain and create machines that truly think like we do. So let's discuss this point together. Thanks, everyone. I'm going to hand this over to the hosts.
Thank you so much, Pete. That was really a fantastic talk, and there was so much to learn there. And it's really great to meet someone who is so passionate about maths and AI, and to give such a really engaging session. So it's also really been really nice to see the enthusiasm and the engagement of all the attendees. I also am really interested to learn a bit more and understand a bit more about what you spoke about. So I'm sure we can hand over to the Q&A session so that we can, yeah, learn a little bit more about yourself and what you spoke about. So just to remind everyone to use the Q&A session, and I see we actually already have we have a few questions here. So Pete, you can use the Q&A session and answer them live. You might want to just repeat what the questions are for anyone who's joining us on the live stream so they can see what their questions are. And there's a lot. Thank you.
Okay, cool. Well, we've got a first question here by Aditi Aran. So, will the trained AI technology like ChatGPT be 100% accurate about topics like predicting stock market prices? Because the sales depend on the amount made by the company and how many people buy it, and that makes it unpredictable. I mean, that's a great question, and I guess becomes a bit of a philosophical point, because if someone is known to be able to predict the stock market, then people would be watching them with a hawk, like with an eagle eye, and then that would then have implications for the actual market itself, and then that becomes an unpredictable model in itself. So yeah, you're right. I don't think we're going to see ChatGPT or anything like that predicting the stock market with 100% reliability. And I think if anyone did have a model, they would make sure that no one ever found out. That's a great question. Okay, how do we determine the number of hidden layers that we need? This is a very good question. And to be fair, I think there are a few rules of thumb that you can use. I mean, you need to have enough weights in your model to be able to learn the estimated complexity of the function that you're trying to model here. The deeper, the more. It's better to have a wider. In general, probably better to have a wider than deeper net. In general, it's probably just easier to train. But there's a bit of an element of being a practitioner here. You don't want to choose too many weights, because you probably end up with an overly complicated model that doesn't train well. We like to mess around and kind of just develop a feeling for these things, and you can see it quickly when you're analyzing how your training's going, and when you're looking at your training loss and your validation loss, you can see how these different models perform with different number of weights. You can also trim things as you go. That's a very good question, and actually comes to the heart of being a good practitioner of AI. You've got to get your hands dirty. You've got to solve problems. You've got to start developing an intuition for these things. Enoch Kumar, what are the possibilities in health or biology? Well, I mean, it's already happening, right? A lot of biohealth sensors that you wear on your watch, like on your smartwatches, they use green, red, and infrared LEDs to do a thing called photoplethysmography to look at to try and measure your heart rate variability, SpO2, things like that. And you'll use like recurrent neural networks and things like that, which are neural networks that have a bit of recurrency, so they can kind of remember some of the previous data they've seen to pick up patterns in the underlying data. There are so many ways that the technology is already used. It's not just using these smartwatches. I mean, as far as I've seen already, some of these AI agents are better at analyzing MRIs. They're better at analyzing X-rays, even than trained radiologists. There's always difficulty with these things, though, and I think one of the main difficulties in AI is that who where does the responsibility lie? If you're working with a practitioner and a radiologist, you're working with someone who's ultimately responsible for making these judgment calls. So in health, what you're going to find is you're going to have AI agents that are really, really, really good at doing these things, but you might just find that people still want a human touch. But it is very exciting because these AI agents, by being able to analyze, things like that, with being trained on data sets of millions and millions and millions of examples that have been carefully labeled by the practitioners, you're going to get very good results out of it. I think the main difficulty really is just in how we incorporate incorporate people's expectations into the process. Okay. Okay, we've got here Noku Makuwaza. How can you guard against AI bias? That's a great question. I think that really just boils down to your training data. And I think, if your training data is selected, if your training data is unbiased, then your model's not going to be biased, right? I think that it ultimately boils down to that. I don't really have a better answer, to be honest. It's a hot topic and it's important to people, but at the end of the day, it's going to boil down to your training data. Okay, how can I get into Cambridge? Like, I'm currently working on my personal project, so what else should I focus on? That's from Mariam Jabari. Mariam, I think it's important to have personal projects. It's important to do, really well at school. Make sure that you are focusing in science, maths, physics. Focus on all your subjects. Make sure you're well-rounded. Make sure you continue to play sports and take part in extramural activities. Just keep doing what you're doing. It sounds like you're doing exactly what you need to be doing. Got a question here from Rafan Khan. Is this capable of helping us to learn more about the outer universe? Well, the answer is yes. There's a huge amount of research going into physics-based artificial intelligence models to try and use physics-based models to help us make discoveries and generalize various areas of physics that are notoriously difficult to solve if you do it through the deterministic way, but through systems of equations and so on. I mean, those things are really, really hard. Like even trying to model the nucleus of a relatively small atom by deterministically trying to solve all the coupled equations, it is insanely difficult. So there's a lot of work going into physics-based AI, and I'm not an expert in this kind of stuff, and this kind of stuff is the stuff that I read about myself just for pleasure. But it looks like a very, very exciting field with a lot of active research. Okay, Raya Latova. Can you explain a little bit more about what is biased data? Okay, well, that's relatively easy. Let's say you're trying to predict well, let's say you're trying to predict the probability of some particular outcome. Like I've got a bunch of ripe tomatoes and unripe tomatoes. And let's say that, the probability of a tomato being unripe that comes from a farmer is relatively low, maybe 20%, one in 5. And let's say that, I train the model on examples where I've only got ripe tomatoes. I've got 96,000 images of ripe tomatoes and 4,000 images of unripe tomatoes. That's biasing my data because it's not an accurate distribution of what is actually found out there. I mean, there are many examples of how you can do this. Like biased data is when the distributions that are present in your underlying data don't accurately represent the distributions in reality, because then you are biasing things. And then your model will learn patterns that don't exist in the real world. It's learning patterns that exist in your data set. So that is a problem. And then, and then what value is your model if it can't make predictions in the real world? Okay. Right, please tell a roadmap for learning deep learning completely. Where should I begin? Well, I mean, to be fair, it's a good question. I mean, the first thing I would do is if you're still at school, if you're still at high school, make sure you pay attention in maths, and pay attention because you need a strong foundation. Now, to be a practitioner, you don't necessarily have to understand all the nuts and bolts of the mathematics, but I would recommend it, right? So definitely pay attention to all the mathematics involved. But then if you want to get into to being a good practitioner, you must get your hands dirty. You have to get out there and actually try and solve problems in the real world. There are so many different kinds of online forums where you can engage in competitions to try and solve problems as efficiently as possible. If you'd like to, I can give a list of options after the talk, but these are the kind of things you should be doing. Like Kaggle, for example, would be incredibly helpful just to, once a week, try and solve a problem, put a few hours into it. Go through some of the winning models because you can look at the models that were used by winners, deployed by the winners in various competitions, and you can learn from them. The only way to do it really is to just get in there and get your hands dirty. Okay, I've got a question from Sana here. What's the impact of optimization of AI algorithms in various fields? What are the risks in optimization? So Sana, I'm not quite sure I understand the question here. Because optimization is obviously got a technical meaning, right? So when you are finding the weights of your model, you're using back propagation to update your weights. And what that is doing is that is an optimization process that is attempting to find the best possible weights to describe the training data. So I'm not sure if you're using optimization in a technical sense here, but optimization is a key part of AI and machine learning because the optimization is the systematic and formal approach to how to find the weights as quickly as possible, and to find the weights that you are certain or have the most certainty are the best weights to describe the problem in general. Okay. Can you explain more the back propagation method? That's from Nur Hamdi. Nur, I don't know if it's best for me to try and describe it because if anything, I should be drawing it. And you can kind of draw it with a straight line diagram just by talking about how gradients work. The way the back propagation works is effectively by using a generalization of the gradient function. And it's a gradient, it's hard to explain. It's almost like a very high dimensional gradient function. Because if you know the rate of change of your weights with respect to your error, then you can then multiply that by your actual error, and you can get a change in your weights. And it's probably easier to draw as a straight line graph and then to try and generalize that into a higher dimensional setting. But backpropagation, if you go online, you can see derivations of it. It might seem a little bit opaque to you because in the backpropagation derivations, they'll include the activation function. There'll be all kinds of summations. There'll be expanding summations. They'll be taking derivatives. But in general, what it is it's using properties of a gradient. And this is why I was saying earlier that having a good understanding of calculus and just being open to how these things generalize to high dimensional spaces is what's going to help you to understand the backpropagation method. But if we get into the details of the backpropagation method, I mean, all we're trying to do is go from the output layer and systematically update the weights at each layer backwards. I mean, that's why it's called backpropagation, because you're starting at the output layer and you're updating backwards towards the input layer. Okay. So the question here, what is DALL-E? Slide picture, anonymous attendee. Well, DALL-E is an AI image generator which generates images from text. Now, this is largely beyond me, to be honest. So I don't want to go into a realm of things I don't understand. But my very, very basic understanding of DALL-E is that it is a diffusion model, which I've heard explanations of, which are hyper interesting. But it's a diffusion model that will take text to go backwards from text to images. And it is a fantastic model and very useful. And if you get your prompt correct, you can get it to generate very useful images like the one I've got shown on this slide here now. Cool. And any other questions? Niha, do I have to learn all the ML algorithms from regression to boosting and bagging techniques, including the underlying mathematics for taking up a career in data science? Well, I think the answer is yes. I mean, you're going to probably want to study data science. You're going to want to study the foundations, the academic foundations of the subject. You are going to have to go through the toolkit and understand how the toolkit works to be able to use it properly. So absolutely, I encourage everyone to take a hands-on approach and to play around with everything and try and understand how it works. And the nice thing is that a lot of the Python libraries that you use, you can go and look under the hood in the Python libraries and start to figure out what they're doing. So absolutely, do pay attention to all of the important tools and tricks in the trade and understand when and how to use them. All right, final question. Ahu, what kind of advice can you give us for being more successful in the future? It's a great question. I wish I knew. I think the only thing you can really do is to enjoy what you do, work hard at what you do, and pay attention and care about the details. I think if success was ever going to come to any one person, then the success would be predicated on how hard you work and how conscientious you are in that subject. So pay attention, work hard, and enjoy what you do. All right, brilliant, guys. Well, I hope I've answered all your questions. Are there any more that want to come through? Cool. I think that's it.
Amazing, thank you. I think we have one person who has perhaps maybe raised their hand. If you'd like to maybe drop a comment in the chat. And if Pete, if you don't mind, just stop sharing your screen.
Of course.
Brilliant. So thank you all for joining us at this incredible session at the Teens in Action Forum. It's been really inspiring to see everyone's engagement and enthusiasm and assuming wonder about as we explored machine learning and the use of maths in this session on machine learning. So I hope that everyone has left with some motivation to learn more about AI, left with new ideas and insights about how to get into this fascinating field. Before we wrap up, I would like to just share some opportunities that you can use to continue your journey with teens in AI. So, as a special thank you for being here today, we're going to offer everyone here a 20% discount on any of our paid courses on learn.teensinai.com. We also have a really fantastic range of free courses, which is part of our skill boosters and talks like Pete's go to build on that amazing session as well. So we also have as I mentioned, an AI for Good incubator, which is a 5-day boot camp where you have to work together with a team of other teams from around the world to pitch and build an AI solution that is designed around a particular SDG. So it's quite a fantastic program. It's one of our biggest that we do have among the IWD. And that is all from me. We will be sharing these details with everyone on email tomorrow as a part of the thank you. So, and I will also just drop a quick message in the chat. So from me at Teens in AI, who's also been joined by Bev, Chi, who actually manages this forum, and also Cindy, who is the host, with Pete and Warren from Sportable. We'd like to thank you all for joining us, and I hope that this talk has empowered you to go forth and learn more and to even lead in AI and technology. So stay curious, keep learning, and remember that the future is actually in your hands. And it was really fantastic to meet everyone this evening. It looks like it was sometimes even late at night for some of you. So thank you for keeping up and joining us. And that's all. Thanks, everyone.
Thanks, everyone.